Hello, welcome to The Naked Scientists at the Cambridge Science Centre. I'm Chris Smith, and this is another of our live events. Welcome. Now, the whole point of these programmes is that this is where you, the audience, become the interviewers. It's your opportunity to give our guest panel, who we will meet in a minute, a really good grilling. This week, we're going to talk about space science. All of our guests this week are connected in some way by the field of space or space science and space exploration. And it's quite pertinent because in recent years, we've actually heard stories about people planning to mine asteroids. We've also heard about people trying to build a hotel, an orbiting hotel in space. We've had a call for people to join a manned mission to Mars. They only want elderly people, though. It's amazing the lengths the government will go to cut the care in the community bill, isn't it? And more recently, they've actually announced, just last week, a proposal was put forward to build a Barber's on the moon. It's going to be called Eclipse. Now, it is, of course, nearly Christmas time. But there is some concern this year over whether Father Christmas is going to be able to make all his deliveries, because there was a bit of a sleigh accident recently. During a test flight, Father Christmas collided with an asteroid. And NASA did catch this with the Hubble Space Telescope. And when they first saw it, they said they think it's a UFO ho-ho-ho. Now, of course, during this programme, we will be obeying all of the laws of physics. Very important, because the penalties for not doing so are extremely harsh. In fact, as the famous astronaut Buzz Lightyear discovered when he broke the laws of gravity, he got a suspended sentence. Let me introduce our panel. Please welcome, this week, we have with us Didier Queloz. He is from the Cavendish Laboratory. We have sitting next to him Alan Tunnicliffe, who's from Chemical Engineering and Biotechnology. And Jerry Gilmore is on the end. He's from the Institute of Astronomy. They're our panel this week. And sitting primed on their experimental bench, Ginny Smith and Dave Ansell, who will be doing lots of exciting interactive demonstrations and experiments for us this week. Let's kick off with you, Didier, because you're famous for having discovered the world's first exoplanet. So you better tell us what one of those is.
Yeah, well, it was almost 20 years ago. And, first of all, I think we should start with the beginning, which is what means this exoplanet. I mean, what is an exoplanet? So we have planets in our solar systems orbiting our sun. And the next question is, we have plenty of suns everywhere. We call them stars. And then the next question is, what about the planet orbiting these stars? So these planets that we have found, and there is about 1,000 of such objects found, we call them exoplanet, and that's my work. I'm trying to understand this object, to detect them first, and then to try to understand how they form and how they are.
Let's put some numbers on this. So in the universe, how many stars are there? Apart from Rod Stewart and Tina Turner, obviously.
Well, it's a difficult number to capture because the universe is so big, so it's difficult to figure out. But we have in our galaxies, it's a bigger structure that we are in, and that's about 100 billion of stars. So, and at the galaxy, there are zillions of galaxies. So you can make up a very, very big number here.
And with that very, very big number, how many planets might there be around all those different stars then?
Well, that was a big question 20 years ago. I mean, we had only our own planets at that time. And the big question is, are we unique? Or are we part of a more bigger set of planets? So I think we have clearly answered these questions. So there are planets almost everywhere. And it's pretty common to find planets on other stars. What is a bit more difficult here is trying to understand how they are, because as of today, we have not really found a planet or a system like our own solar system.
Like the Earth at all?
We have found kind of objects that look like the Earth, but they are not really exactly like the Earth. That's a big problem then.
How do you find them?
Well, I think here this is a good time for the experiment. So the problem we have with the planets is a very simple one. I mean, the planet is orbiting a star, and the star is extremely bright. So if you take any mean to make a picture, you will only see the star. So you have to find tricks to try to see something which is almost invisible. So on the practical sense, I mean, when you have a planet orbiting a star, what you do have, and this is a nice experiment here, because the planet is very light, I mean, Jupiter, which is the biggest planet we have, is only 1,000th of the weight of the sun. So it's very tiny. Then when you have the planet orbiting the stars, what you do see here is practically all the system is orbiting around what we call the center of gravity of the system, which is, in the case of the sun, almost in the middle of the sun. It's a little bit, it's still in the sun, it's a little bit aside. So there is a tiny motion that the sun is doing by the fact there is a planet. So you do obviously see the motion of the planet. We call that the orbit. We know that the Earth takes 1 year to go around the sun. But because of the Earth, the sun is doing a tiny bit of motions. And then these motions, this is what we have been using to detect a planet.
So when you say there's a little bit of motion, the sun wobbles backwards and forwards a little bit because the planet going round it exerts a gravitational influence on the star.
That's a perfectly right way to express this. Exactly.
So we're showing this over here. Dave set up this wonderful example. It's not quite what you'd see if you had an actual star and an actual planet.
Let's be honest, it's a doorknob on a stick, isn't it?
Yeah, so we've got a nice gold doorknob to represent the sun, shiny, bright. And we've got, is that a ping pong ball on the other
It's a
end?
ping pong ball, yes.
And we've got a ping pong ball on the other end of a stick. Now, what Dave's doing is he's got that on a piece of string and he's spinning it. And you can see that this means that the ping pong ball is going round and round the doorknob. The piece of string isn't ending up in the middle of the stick like you'd expect if it was a similar weight on both ends. It's actually orbiting around the centre of mass.
And so this means that if you look at the doorknob is wobbling in the same way that the sun is wobbling because the Earth is orbiting it. There isn't actually a stick between the Earth and the sun, of course, but the physics is very similar with gravity and a stick in this particular case.
So the sun's actually doing a little bit of orbiting itself. This seems very simple with just one planet, but I can imagine it must get very complicated if there's more than one.
Yeah, it's a bit like a watch after. I mean, you have a needle that takes the hours, the other one the minutes, and then the seconds. So it's like a watch. I mean, you can read through it if you have enough time to watch the whole motion of the whole system. That's what we need to do if you want to capture the longer period system.
What do you use to spot these wobbles?
Okay, that's a second big question, because what we have seen here is a principle of the motion. And the problem is, what do you do to detect that motion? That's not at all obvious. So there is a simple trick that we can use, which is related to the light. I mean, the light is about like the sound. It's a wave. And then if you move an object, the sound will change. So there is a tiny difference in the wave. We can see it as a change of color. And then because of these motions, this will create a kind of a tiny change in the color in the waves. So we can see this experiment that just tried to show this instead of having the light, which is just too fast, but using the sound.
So we've got another really high-tech experiment for you here. We've got a ball of bubble wrap with some kind of alarm inside, you said.
It's a buzzer I bought this afternoon.
So we've got a buzzer in some bubble wrap, and we're going to put that in a canvas bag. You can see how high-tech this is.
So this is going to make a horrible noise. So I'm going to explain what I'm going to do first before I turn it on. I'm then going to whirl it around my head. And if you listen to it, you should be able to hear a slight change in the pitch of the sound as it goes round. So let's turn it on.
And I'm going to get out the way because I don't fancy being hit in the head. Did everyone hear that?
So as the bag was moving towards you, the pitch went up slightly, and as the bag moved away, the pitch went down. As Didier was saying, the same thing actually happens with light. The physics is slightly different because Einstein and relativity gets in the way. But if it's moving towards you, the light gets slightly bluer, and if it moves away from you, the light gets slightly redder.
Yeah, that's exactly what we're doing. We're just detecting this, but then it's a tiny change of the light, and that's pretty tough to
But you're
do.
not using a shopping bag and a buzzer.
No,
are
we
you?
don't use that. I mean, this is what the difficulty here, because we're talking about tiny motions and picking up such a tiny motion. I mean, if you take the Jupiter, for example, it's the speed of the running man. So it's really tiny compared to the speed you encounter in space. So it's really tough. And then the equipment that we needed to build to measure the speed change, I mean, could not be built before. So we had to wait so long to build such a first experiment that was doing that. And that's what happened 20 years ago.
So Didier, you've said very nicely how you detect these planets, but how do you work out whether a planet's, say, like the Earth or not?
Yeah, that's another aspect of the detection. So in some case, you can be lucky enough to have the orbit of the planet crossing exactly the disk of the stars. Then it's called a transit. This transit, I mean, it's a kind of a shadow that is produced by the planet on the stars. So you don't see the shadow itself because the star, you don't resolve it. So you don't see any picture of the star, but you see a tiny change in the light of the star. Like if you have a clouds passing in front of the sun during the day, and you don't really see the clouds, but you feel that there is a tiny difference in the light. So it's exactly the same. And from that slightly drop of light, you can get the size of the planet. So if you can get some way to weight the planet, like with the technique that was described before called the Doppler technique, and some way to size the planet, so you get two very fundamental parameters of the physics. One of them is the mass, and the other one is the size. So if you get the mass and the size, you can build something which is a bit magic, which is called the density. And with the density, I can tell you whether it's like the water, whether it's like a gas, or whether it's like a rock.
Okay, let's take some questions. So you need to get your thinking caps on for your questions. What have you got in the email, Ginny?
So I've got an email in from John Black, who actually picks up exactly on what you were just talking about. So he asked, if you're using that kind of method to detect planets that are travelling in front of a star, so you're looking for the shadow, does that only work for planets that happen to line up with the telescope and the star? And can we find out about other planets that don't line up?
Well, yes, you have to be lined up to get the shadow effect, otherwise you don't get the shadow. But there is something interesting, which is called the phase effect. I mean, we do see the moon, the light from the moon changing because the position of the moon is not the same. It's not the same light from the sun. So you do have such effect as well on other planets. So you don't need exactly to have a transit, but at some time of the planet gets a lot of light, and the other time the planet, show you only the dark phase. So if you have good telescopes, very accurate, because this is a very tiny change, you can see that. It's called the phase effect, and it's a way to probe the clouds on the planet. And in that sense, we do a little bit of weather on these planets by doing this way.
Amazing. Let's take your questions. What's your name?
Helen, I'm from Cambridge. You were saying, of the exoplanets that we found, how big is the largest group that are all going around the same star?
We have a lot of what we call multiple systems. And what we do see is when we have small planets, because we're finding small planets between the Earth's mass and Neptune's, they are very often with others. So we have really a series of what's called compact systems made of many planets. So I think the system that has the most of the planet these days is maybe 6 or 7 of them. And it doesn't mean we have found all of them. We find the easiest one, which is the one known by the stars. So there may be much more. And we clearly don't know, how many planet maximum you can get in the system. But it just depends on the mass. And there's a lot of mass to build a planet at the beginning when you form a system.
My name is Kai and I'm from Cambridge. Is there any way to tell, say, if there's like a liquid within a solid, like lava, like in the center of the Earth?
This is a very good question. We would love to know this. The only thing we can do right now is to get broad perceptions, whether it's a big planet like Jupiter, made of gas, or if it's a rocky planet like the Earth. Now, if you start to mix up all everything together, you can have a kind of a mix of everything, because you can have a planet that have a core that would be very heavy, like the iron core, and then you have what's called an envelope, which is a bit less, which is like the lava you have on the Earth, and then you can have an atmosphere that could be made of water. You can imagine a planet that doesn't exist in the solar system where you have a huge water oceans that's not only 10 kilometers, but can be 500 kilometers. So you can have a lot of many mixed ways to build your planet. So answering exactly your question will take some time. We're designing experiment right now to trying to probe and to detect some what's called feature, what's on the surface of the planets, and trying to exactly to know that, because the water, for obvious reason, is kind of a thrilling prospect to get water on other planets.
You're listening to a special edition of The Naked Scientists, recorded with this amazing audience at the Cambridge Science Centre. My name's Chris Smith, and with us this evening, Ginny Smith and Dave Ansell are experimentalists, and our panel of esteemed experts. We have Didier Queloz, we also have Alan Tunnicliffe and Jerry Gilmore. In a second, we're going to be finding out about life in outer space and what can survive the rigours of space. But right now, we're talking with Didier about finding exoplanets. Ginny, what else have you got on the email there?
So I've got an email in from Angelita Mills, who wants to know why poor Pluto was demoted from being a planet.
Oh, this is a very interesting question. You have to
should we take a vote on that first? Who thinks Pluto deserves to stay as a planet? Overwhelming response. I was very disappointed. Were you disappointed when Pluto got demoted? Yeah.
So I have to tell you why, then.
So it's
This
your
is
fault.
scary. We have to go back to the history of the solar system. It's a very fascinating story. You have to realize that for a long time, the knowledge of the planet was only related to the capability to see planet by the eyes. And then it took a long time to move away from that time. With the telescope, then you expand it and you get Uranus, and then using Uranus, you detected Neptune's. And then it took quite a long time for people to figure out exactly what was next. And then the problem of Pluto is it's not alone. I mean, the region of Pluto has been probed when Pluto has been discovered, but they also probe other systems, other planets at that time that was demoted as a planet. One of them is called Vesta or Ceres. This one's planet, this is our object that are as big as Pluto there. So all these objects are not planets at all. So Pluto is exactly in the same situations because it took a long time after to figure out that there are other kind of objects like Pluto. So the problem is then, what do you do if you start having not only 1, 2, 3, but 100 of systems like that? And that's these 100 systems deserve a specific name, which is called the trans-Neptunians. So beyond Neptune's, there is not only Pluto, there is tons of objects. And that's the reason why at some point we have to decide what we do there. Do we continue to count them, and then we ended up with 100, 200 of such objects? Or do we define the planet as an object that is kind of isolated? And that's exactly what happened in these big discussions. So people have agreed that at some point a planet, to qualify as a planet, it's a bit a tough discussion, but it's kind of has to clean everything around it. So if there are other objects that you find between Mars and Jupiter, it's called the asteroid belt, so it doesn't qualify as a planet. And that's the reason why Pluto has been demoted.
You know, that's an astronaut's favourite music, Neptune's. Got a question down here.
Oh, hello. My name's Paul from Cambridge. You've been looking for planets, and I suppose that's partly because we all know what a planet is. But have you, in your searches, found anything that's very different to what you were expecting?
Well, I think we have been surprised from the beginning, and we keep being surprised. The reason why is when we started all this, we had this obvious mental picture of solar system planets. And all the planets that we're finding are very different. The first one was a big Jupiter, very close to its star. It's kind of a burning world. So there is no counterpart for these systems. Now we have what's called super-Earth. It's kind of a very rocky, very hot planet, kind of different from the Earth. We think that this is a big core of rocks and with a big atmosphere of lava. And again, it's a big surprise. So they all have planets, but they are not the planet the way we see that in the solar system. And I think this is just the beginning of the story.
David from Cambridge. If we were to hypothetically position ourselves on the nearest star in our galaxy and using technology that we have available today, look towards our own solar system, what would we be able to understand about our solar system?
I think today we will not see anything because we're just on the verge to detect a system like our own. We do have found a lot of other systems, and the interesting part of it is we know that from all this system that we have found that the vast majority of the stars, they do have such a system. So we know already that the solar system is not the vast majority of the other planet, but it doesn't mean that there is no such a system. So today we would just fail. The big problem we would have is Earth is very tiny, but then even Jupiter will be a big problem because to get Jupiter, you will need to observe our system long enough, and then you will face the activity of the sun. There is a solar activity, solar cycle, and we know that the sun, when there is a high activity level, can be pretty active. There are a lot of spots on the sun, and that prevent us to really do something good to detect planets. So today I must admit that we will just miss the solar system.
That's reassuring, isn't it? No one's going to come visiting too soon. Ladies and gentlemen, Didier Queloz. Our next guest is Alan Tunnicliffe, who's from Chemical Engineering and Biotechnology, and he works actually on things that can survive in really quite bizarre environments. Tell us about this work.
Well, we work on organisms, creatures that can survive desiccation. So that means they can dry out, they can lose essentially all their water. And that sounds like a pretty bad thing to happen, which it would. I mean, for us, we'd die pretty quickly if we started drying out. But there are some creatures that can do this, can lose all their water and survive. And then you just add water again and they come back to life and carry on as though nothing had happened.
What are they?
A wide range of things, lots of microorganisms, lots of bacteria, yeast, for example, which you might see a little bit later on, or perhaps already. Yes.
Yeah, in fact, let's get it set up now. So we're going to show you how you can bring some animals, some creatures, back to life. So we've got in these little pots just some normal, fast-acting bread yeast and a little bit of sugar to give them some food. And what we're going to do is we're going to add some water to them, rehydrate it, and we've got them in film canisters. Now, young people amongst you might not recognise these. They're remarkably hard to get hold of these days. Now everyone has digital cameras. This is what you used to get film in, and they're very useful for science experiments.
So I'm just filling them up with water nicely, and I'm going to put the lids on, and then we will leave them for a bit, see if we can reanimate that yeast.
So we've given them some nice warm water, and we're going to put them in the bath of warm water. Do you want to put the bowl on the front, just so no one can miss it if something exciting happens?
I'm glad it's in front of Alan. So these creatures that can do this, why have they evolved to dry out?
Well, it's part of the natural environment. If you think about a yeast living on the surface of some fruit, then they are going to experience drying conditions. It's quite hot in the sun, the wind blows around them and takes all the water away. So they need to be able to cope with this low level of water and survive.
So when something does dry out, what actually happens to the organisms when their cells lose all their water?
Well, we need water to have any biology at all. So they basically shut down. They go into a state of suspended animation. It's as though they even stop aging. So animals will do this, and they have a natural lifetime. And when you dry them, that stops, and they stop aging at that point. And then when you rehydrate them, they will continue aging, and then they will live out what's left of their natural lifespan after that point.
So what is the relevance of these creatures to space?
Good question. And the point is that there's not much water in space. Okay, so if you were thinking about organisms moving from one place in a solar system to another, from Earth to Mars, or the other way around perhaps, an organism like a yeast is not going to build itself a spaceship. So it needs to be able to survive that journey without the presence of water. So if it can survive drying, there's a good chance it will be able to survive the journey through space. Because the other thing that happens when you have this drying process, when you get this sort of shutdown of all the biology in the organism, is they become very resistant to stresses. So a dried yeast, for example, is able to survive vacuum, as in space. It's able to survive very, very low temperatures, even close to absolute zero, which is what you'd find in space. So that's exactly what you would like the organism to be able to do, to become very stress resistant.
A lot of radiation in space, though, isn't there?
That's the problem. So you need to be able to shield the organism from radiation, but that may be possible.
Dare I ask, has anyone actually tried seeing if there are organisms capable of surviving in space?
Yes, indeed. So people have sent up various organisms, for example, bacterial spores, and some dried little animals of the type that we work on, water bears and rotifers and things. And you can put them on satellites or International Space Station and have them exposed to space conditions. And there have been bacterial spores going around the Earth for several years and yet surviving that process. So they can survive.
So it's like C. diff can survive in the hospital. These things can even survive in orbit. So,
yes.
So when NASA and other agencies say they take steps to make sure that what they put into space and send to Mars doesn't pose a microbiological threat, in other words, they go to enormous lengths, don't they, to clean satellites and other objects off, then that's reasonable practice.
Yes, if you don't want to contaminate the environments that you're visiting, it's a good idea to do that.
Ginny?
So I've got a question here. Alan Scott, who actually got in touch on Facebook, and he asked, could we engineer DNA to send to a planet if we found one with the right conditions? Would it survive, and could it then seed life?
So, if you take the right steps to protect the DNA from radiation, as we just heard, you could, in fact, get DNA from one place to another. Oh, okay.
I think our experiment just worked.
Well, it didn't quite launch into space, but it's...
It now looks like Alan is sort of thrown up on the table in front of him. Ginny, what's going on?
So what
There's the other one.
I'm just going to pass some tissues to our guests so they can tidy up if they need to. So what happened there? Well, our yeast was coming back to life. Once it had the water in there and it had some sugar, it could rehydrate, it could start to grow again. And what yeast does when it grows is it produces a gas. So it's produced carbon dioxide that's built up in this little film canister. And then film canisters are pretty good. They can keep quite high pressure, but at some point, they can't hold it in anymore. The lid popped off, and we got a nice big explosion.
And fountain of yeasty broth.
This is a special edition of The Naked Scientists, which is being recorded live at the Cambridge Science Centre with me, Chris Smith, with Didier Kello, with Anne Tunnicliffe and Jerry Gilmore, and our science experimentalist, Ginny Smith, and also Dave Ansell. And, of course, you're in the driving seat because you're asking all of the questions this week. We're talking about space science, and we're talking about the possibility of things surviving in space. So there's one theory, Alan, that says that life got started here on Earth because something delivered life to Earth. Do you believe in that?
It could have happened. People talk about the life on Earth arriving too early in a way. I mean, it may have been as much as only 500 million years after the Earth was formed, and that some people think that's too early. So how could that have happened? Well, we might have got a helping hand by life being seeded from elsewhere, perhaps from Mars.
I mean, is there any evidence that things could get into rocks and things and then survive being blasted off of the surface of one planet across space and then land on another and not get destroyed?
Not quite that, but people have done experiments with bacteria which have been buried inside rocks, and they've tried to mimic what would happen if you had a meteor impact and blasted that rock into space. And people have shown that the bacteria that they've used survived that process. So possibly yes.
Anyone got any questions?
I'm Jeff, also from Cambridge. What's the largest size of creature that can survive being dried and brought back to life again?
There's a creature called Polypedilum vanderplankii, which is basically... It's a midge.
Easy for you to say, yeah.
Well, it's not a very attractive organism in a sense. It's just a midge, just very boring. But it's interesting. It comes from Africa, and its larval stage is able to survive desiccation. And the larvae are quite big, They're about half a centimetre in length, something like that. And that's the largest one I know of that can survive desiccation. The problem is, once you get larger and larger, there are sort of physical stresses on something as it dries out. It gets very sort of brittle and crumbly. So if you try to do that with, say, a human being, we just wouldn't survive physical stresses of drying. We just crumble.
Dave and Ginny have got an experiment coming up, and they're going to have a go at it.
Hello, I'm Carl. I'm also from Cambridge. You say that water is necessary for life, but isn't that just life as we know it? Couldn't there be different life in space that doesn't depend on water?
Oh, absolutely, yeah. I mean, everything we say is from a sample of one, right? All we know about is life on this planet. And so, who knows? There could be other types of life out there.
I've got a question in from John Michael Williams, who wants to know whether the very high levels of iron on Mars might prevent life there.
Just looking at what happens on Earth again, which is the only example we have, there are lots of organisms that can survive and grow, in fact, in the presence of elements, lots of iron and other types of heavy elements. And they've evolved ways to live with that. So in principle, no, that's not a problem.
David from Cambridge. When I was at school, we were taught that all life derived its energy ultimately from the sun, and life wouldn't be possible without that. We've since discovered sulfur-eating bacteria and undersea vents. Has this changed our opinion on the chances of finding life in other places in the solar system and beyond?
Yes, I think it has, in the sense that people think about Mars as our closest neighbour, and we're interested in the idea of life on Mars because we think there was water on the planet, surface water on the planet at some point in its history. And therefore, life may have evolved on Mars during its early life. The question is, what happened to it? Well, it's possible that the life, if it did evolve on Mars, is still there, but surviving not on the surface, but underground. So we know that, if you look at the Earth again, we can see bacteria which survive, grow, live quite happily several kilometers under the surface of the Earth. So they live within the rocks, and there's enough water there for them to survive and get by. It's a bit warmer down there, and actually the temperature, that it gets very hot as you go towards the center of the Earth, is the limiting factor of how far bacteria can survive down there. So if you think about Mars, then maybe it also gets a little bit warmer as you get towards the core, so there may be liquid water underground. And so if life did evolve on Mars, there's no reason why it shouldn't still be there, but not on the surface where we're looking for it, but maybe some distance underground.
Is it possible then that we'll be able to work out how to put humans into a suspended animation state, a bit like they do in sci-fi films, so you can go on long space journeys so that we can head off to Mars or wherever else we want to go?
Well, not by drying them. That's not going to work. We're actually trying to do that with human cells, actually. But so you could dry a human cell, which you can grow in the laboratory, but not a whole human being. Maybe you could use freezing instead. That's probably the best way to go.
Especially in this weather. Any other questions from you guys?
Hi, Helen from Cambridge. What's the longest period of time that anything has been desiccated and then successfully reanimated that you know of?
Depends on the organism. So if you're thinking about these little animals that we work with, which are tiny little invertebrates, anything from 10 to 100 years. But those are only the well-documented examples because you're relying on having museum specimens and so on that you know the age of and that you can look at carefully. There is evidence that some microorganisms, some bacteria, may be able to survive for much longer periods. Some people claim even 200 million years, which I think that's not really well substantiated. But we're talking about long periods of time. Certainly enough time, we think, to transit between planets in the solar system.
Hi, I'm Robin from Cambridge. I just have a question with desiccation. Is there any change in the organisms in that time when they are kind of shut down? Or do you just come back exactly how you were?
We think that the organism is basically unchanged. For biochemistry to happen, which is how things break down, degrade, how you get older, you need water. So if you take all that water away, those biochemical processes, including aging and other processes, cannot take place.
Hi, I'm Melanie from Cambridge. All the kind of things you've talked about so far for going between planets, it's kind of just suspended. Do you think there's any chance that you could have life which actively lives not attached to a planet?
As far as we know it, and we had the question about other forms of life, but the form of life that we know requires liquid water. So you'd need to have a situation where you can guarantee liquid water. And the temperatures that you find in space are way too low for that to happen. So you would need a protected environment like a spaceship in order for life to survive in space.
What about a planet that doesn't have a star and just goes wandering through space? Because we've found some of those now. I mean, Didier, in the recent month, we've had a report of another one being found of just a planet with no star, and it's just wandering through space.
I mean, we don't know exactly how much there are of these planets, but clearly in the mechanism to produce a planetary systems, some case you can be unlucky, and because of the big interaction between planets, you may have a change in the orbit, and some of them can be just thrown away into space. So there must be such a planet going around that is very cold, extremely cold. That's why we don't see them, because they are so cold that they don't emit anything.
Any other questions from you guys? There's one just at the back over here.
Good evening, it's Carlo from Cambridge. I would like to ask how gravity may affect living forms. Is there a gravity range where we believe life can develop?
People have put living creatures into space in a spaceship, humans of course, but also other creatures. And there are some processes which may be slightly affected, so development of the organism from an egg to a fully grown organism might be affected somewhat, but basically most of the things seem to happen okay. I mean, if you're a bacterium, you're probably not going to notice too much that you're in a microgravity environment.
I guess the bigger you are, the more gravity affects you, so the narrower range of gravities which you function on. So if you're an elephant and you went to the surface of a planet twice as big as Earth, then you'd have trouble.
Well, you'd have to adapt to microgravity, I think, which is the question. And so if you're an organism that's evolved to live on a planet with significant gravity, you're going to find it quite difficult. And astronauts that go into space have problems with their bone density and muscle tone and so on. So it would prove quite challenging, I think.
A weighty question. Anything else from you guys?
Hello, I'm Brian from Cambridge. When we send astronauts up into space, they have a closed environment for maintaining water in. Is that 100%? Is there a limit to how long you can send astronauts into space preserving the water they've got, or do you need to send up a water supply to keep them going?
Gosh, what a great question. So I imagine you could do this for quite a long time. People are talking about very long missions indeed, missions to other stars and things. And to do that, you would have to be able to recycle your water and maybe, yes, even regenerate it to some extent.
I'm Sam from St Ives. If there was a planet with an atmosphere with gravity, if the planet moved, would the atmosphere move with it, or would it stay in a cloud?
I think there's one for you, Didier.
Actually, because of the gravity, the atmosphere is a bit like us. I mean, it's a bit difficult to get out of these planets. We need the rocket to get out of the planet. So the atmosphere is kind of glued by the gravity to the planet as well. It's exactly the same. The only part of the atmosphere that can get away if you have a very light molecules, and some of them, I mean, the hydrogen or the helium is used for balloon. And then this one can just escape in some conditions. But most of the gas, they just trap like us to the planet.
Can I just ask a question, Didier?
You're authorized to do that?
This is the only chance I'm going to get to ask this question. So gas is escaping from the planet, right? So why doesn't our atmosphere just all disappear into space?
It's a matter of two actions. One of them is called the gravity. So if you get the planet light, not strong enough, with enough gravity, then you're going to lose the atmosphere. It's a bit what happened with Mars, which is a very small planet compared to the Earth. And then the other situation when you can get trapped is you're too close to the sun. But then there is interaction in the upper atmosphere between what's called the solar wind, because there is interaction. The sun is producing particles, not only radiation, but also particles. And then you interact, and it's like a blowing wind that slowly kind of grind and blow out the atmosphere. And if the atmosphere is very thick, but the planet is very close, if you get enough time, you can completely peel off of the atmosphere. And we do believe that we have now some very weird, you may have heard about rocky planet made of lava orbiting the stars in one day. So they're so close, I mean, they can almost touch the stars. And we do believe that these planets must have been bigger and kind of have lost their atmosphere because of the impact of the sun.
Lovely. Any more questions?
Hello, it's Victoria from Cambridge. If we're talking about exophiles and change in pressure, if we took some of the bacteria and the creatures that are living in hydrothermal vents deep under the sea and we brought them back up to the surface, would they survive, or would the change in pressure be too great?
That is a problem. These so-called barophiles, these organisms which like living at high pressures.
Like in our lab.
Different kind of pressure. But yeah, if you try to bring them up to the surface where the pressures are what was are normal, for them, of course, it's not normal. So we think about these so-called extremophiles living in these crazy extreme conditions. But of course, to them, living there, those are the normal conditions. And what we live in is an extreme environment to them. And that's why it's difficult to work on those organisms, because you have to try to replicate the conditions that they would normally live in to be able to study them.
Alan Tunnicliffe, thank you very much. This is a special edition of The Naked Scientists, which is recorded live on Wednesday, the 27th of November at the Cambridge Science Centre. My name's Chris Smith, and also here with us, Dave Ansell and Ginny Smith are doing some experiments. You, a wonderful audience, are here asking all the hard questions of our wonderful panellists, who are Didier Queloz, also Alan Tunnicliffe, and our next guest, Jerry Gilmore, who is from the Institute of Astronomy. Tell us about your work.
Hi, I'm Jerry from Cambridge. I'm one of those very rare astronomers who actually tries to understand things that you can actually go out and look at night. There's not many of my colleagues who do this, and most of the time I don't either. But in particular, I've got a huge project that's coming into fruition right now to try and understand the origins of the Milky Way. So it's the most basic question you can go outside and answer, or ask at least. Every culture that we know of has its own answer. We call mythology or gods or whatever name you like, as to how to break the what came first problem. Here we are, what was there before us? And so the challenge is to say, look up at the sky and you say, well, I can see what I can see. But what's really out there? What is the Milky Way really made of? How big is it? How fast is it moving? What is there out there that's important but doesn't shine that we can see? So how much does it weigh? And a few basic little sort of homegrown questions like where did the oxygen that you are breathing right now get created? And how did it get here from wherever it was formed? And how's the stuff you're made of got to be around so that you can be made of it?
Can you give us a few stats on the Milky Way? In other words, where we are in it, how big it is, how many planets and stars it may have, that kind of thing?
Well, that's really what this project I'm going to talk about, Gaia, is going to answer. But our approximate number at present, the Milky Way is made of roughly 100 billion stars, of which the Sun's pretty typical. The Sun is about 30,000 light years from the centre of the Milky Way, and the far outer reaches of the Milky Way that we still think of as the Milky Way are about a couple of 100,000 light years from the centre. So the whole show's 300,000 or 400,000 light years across. It's a big thing. It's made of 100 million stars, but mostly it's made of dark matter. About 90% of the Sun is stuff that's not the same as what you're made of. It's something mysterious that we know nothing about except that we can weigh it. And we know that a star like the Sun, which is made of the same sort of chemistry that you're made of, is pretty typical. And so most of the stars and planets are made of the same sort of chemistry that you are. But some parts are made of quite different things, really primordial stuff that's left over from the very early stages of the Big Bang. And so that also tells us how old the Milky Way is. The whole universe is about 13 billion years old, and it's pretty clear that the first structures that eventually came to form what we now call the Milky Way were already in place a few 100 million years after the very beginnings of the universe. So, of course, it's even older than that. The hydrogen in the water that you're made of was created in the Big Bang. And so, in a very real sense, you are a fossil of the Big Bang itself. You are.
Do you think the
13
water
billion
companies
years
will
old.
kick in and try and charge us for that?
Yeah,
The
absolutely.
bills are going up. So, one question though is, if you've got all this matter which is coalescing into stars in this galaxy, why does it spread out into separate little stars? Why doesn't it just form one massive blob of matter?
Oh, well, that's because the universe is a big place, actually. And the challenge in astronomy is not to stop everything forming one giant thing, which would be a giant big black hole. It's quite the reverse. It's how to get it in close enough that it actually has stars so that you can see them in the sky. In the very early universe, the whole universe was very uniform, but it was noisy because of the Big Bang. And the sound waves, they really were sound waves, there really was a bang. Those sound waves push the matter around and allow it to accumulate and then fall together. So good old gravity, the dominant force in the entire universe, eventually brings stuff together. But ordinary matter, ordinary gas and so on, doesn't like being in a small place. It's really hard for it to cool down and collapse into a small place and then form stars. So to do that, you need, first of all, you need chemistry to cool the matter. So you get this chicken and egg problem. If I don't have any chemistry to form the first stars, how do I form the first stars? And that's a question that we're thinking about right now. But then things do form stars, but the thing that stops it all going crazy is, again, the dark matter. The dark matter dominates the weight and the mass of everything. And there's so much of it that all the stuff in the universe is whizzing around quite fast. And it's whizzing around so fast that it never gets a chance to accumulate into very large pieces, largely because one side of a large blob is moving quite fast relative to the other side, and it just shears itself apart. So if I tried to put all the Milky Way together into a single thing, it would rapidly fragment again into what we see.
One physicist put it to me that the only reason that dark matter got invented is so you could put the word dark in front of it. It sounds sexy and you get more grant money. But there we are.
That's true for dark energy. It's not true for dark matter.
Tell us about actually what this Gaia project is. How are you trying to map out the Milky Way and understand it?
So Gaia is the name of a satellite that gets launched on December the 19th, about 9:15 in the morning. You'll read about it in the news that day, hopefully, as a wild success and triumph for 25 years of my life.
You notice we're recording the programme before the launch of Gaia, just in case, because otherwise we wouldn't have been able to use Jerry on the show, because he would have been talking about the satellite that wasn't.
Otherwise, you'd be hearing sobbing noises, but it's going to work. It's astonishing technology, actually. It'll just blow your socks off. But the real thing that Gaia is going to do is take the first ever census of the Milky Way. At present, we can't do that. We can take pictures of the sky and count the stars, get this 100 billion number. By eye, you see about 6,000, so that's a teeny fraction of what's really out there. But we don't know where they are. We don't know how far away they are. And the hard thing in astronomy is measuring distances. There's only one way we can do it, and that's by using a triangulation technique called parallax. That here is an experiment that all you listeners should be doing right now. Hold your arm out in front of your face. Come on, audience, hold your arm out. That's it. Now close one eye and then close the other eye. And you'll see your thumb, hold your thumb still, and you'll see it apparently jumping from side to side. Now that's parallax. And that tells you, the amount it moves tells you how long your arm is. And all animals have evolved that way, so you can find out where the food is, so you can go and catch it. And that's the same trick we use in astronomy, except in astronomy the distances are rather larger than they are to your nearest dinner. And so we need to measure much smaller shifts, and that's where we need fancy technology. And in fact, the scale is such that the distances in the universe are so large that Gaia measures angles has silly names, nanoradians and things that only a nerd would understand. But to give you a useful analogy, the accuracy with which Gaia will measure the positions of each star is equivalent to locating a shirt button on the moon. So it's equivalent to measuring the thickness of a human hair when you are sitting here in Cambridge and the hair is on somebody's head in Paris. So that's the level of precision. It just blows your socks off, doesn't it? I mean, it's awesome, this thing. And Gaia's going to do that for 1 billion stars. And so it's going to provide this 3D map of where these billion stars are. But it's going to do even better than that, because we're going to carry on doing that for 5 or 6 years. So we'll see how they're all moving So we'll not only get a 3D map of where stuff is now, we'll also know how it's moving. So we'll know where it's going to be in the future, and we'll know where it came from in the past. And we're going to do even more than that. Why stop there? So while we're at it, we're going to actually deduce the properties of those stars and work out what chemical elements they're made of. So we'll be able to track back the history of the oxygen, the carbon, the nitrogen that you're made of, and find out what stars made this stuff and when and where and how it got to be in our bit of the universe, and how the Milky Way is still forming today. The Milky Way is still growing. It's like some people in this room. Most of us are actually probably either growing or putting on weight. And the Milky Way does it too. It's getting heavier every day. It's gobbling up its neighbours, which I hope you're not doing. It's not...
Not yet.
and so it gets bigger and heavier. And Gaia will find these, no matter how cleverly you try and eat your neighbour, you'll always leave a few crumbs around. And Gaia will do the same thing. It'll find the crumbs and the debris of these little satellites that are being gobbled up. And so we'll be able to count the things that used to be alive and have now been gobbled, and work out just when and where the Milky Way put itself together.
Let's take some questions. So get your thinking caps on, but in the meantime, what have you got an email there, Ginny?
So I've got an email from Patrick Mond, who says he's heard about a planet which was inventively named Planet X approaching Earth, and he wants to know, if a new planet did enter our solar system, how would it affect us here?
Yeah, people spent ages looking for Planet X, and then they eventually found Pluto and realised they had found Plutino X, as we heard just before. It's kind of cute. And there will be more Pluto-like objects in the far outer solar system. The way we find them is the way we find anything else, is by weighing them. It's the only way we can find things that we can't see, is by weighing them. And so you say, how can I weigh something if I can't see it? Well, you then say, well, let me tell you about dark matter, but that's a different question. But the key to a Planet X thing is that there are lots and lots of asteroids. In fact, Gaia will measure very carefully the orbits around the Sun of about 40 million asteroids. And some of these go a long way out. And so if there is an extra planet out there, then Gaia will notice that all the asteroids coming from that direction in the sky have slightly funny orbits compared to the ones coming from other directions in the sky. And so by looking for patterns in the asteroid orbits, we'll be able to tell you what is there, or equally what is not there.
That's how a spaceman keeps his trousers up, of course. Asteroid belt.
Hello, it's Victoria from Cambridge. When you talk about the size of the Milky Way, are you talking about it as in like a 2D frisbee or more like a 3D sphere? Like, how do you picture the Milky Way in terms of size?
All of the above is the answer to that one. Aren't I annoying? The Frisbee picture of the Milky Way is a very good picture of how the stars are distributed. That is actually very realistic. We all take it for granted, but that's only because we were told that was the answer. Newton failed to deduce that. He tried very hard, and it was one of his great failures in his life, was to try and work out the structure of the Milky Way, so he gave up astronomy and moved off to run the mint. But about 100 years later, a guy named William Herschel, working in the exotic astronomical centre of Slough, did actually produce a proper star map of the sky and deduce this Frisbee structure. And so that appreciation that the Milky Way as a Frisbee is actually quite modern. But that's only the stars. The dark stuff and some of the very oldest stars are actually distributed in it's not quite a sphere, it's more like a rugby ball shape. You can tell from my accent I go for a rugby ball as an analogy. But most of the mass, the real stuff that's out there, reality, is in a big rugby ball shape. Most of the stars, the uninteresting bits that we can see and you and I are made of, that's in the big Frisbee.
He didn't say anything about cricket, though, did he? You notice that? Who's next?
Jeff from Cambridge. Can you tell us a bit more how Gaia is actually going to see these things? Is it a camera? What is it doing when it's out there for these 5 years, discovering these billions and billions of stars?
Well, there's a famous quote from an American sports coach who says the best way to find out what there is look. And so that's what we do. The first simple thing, the only basic step you take in any experiment, but especially in astronomy, is going to take a picture. And so that's what Gaia does. Gaia is just a gigantic video camera. There's 2 telescopes mounted on a big ceramic ring. And it's got 2 telescopes, and these 2 telescopes feed light onto a gigantic video camera, which is the largest video camera ever built. So it's made of CCDs, just like the ones you have in your mobile phone, except the ones in your mobile phone have a CCD in them which is about the size of the nail on your little finger. The Gaia camera is about the size of a large desktop. It's over 1 metre long, 0.5 metre wide, and it's got 1 billion pixels. So it's the biggest camera ever built. And this 1 billion pixel camera is just going to be taking pictures, doesn't it sound easy, and beaming the information down to us for 5 or 6 years. Now, from these pictures, we can measure how bright the star is and where it is. And if we keep doing that for 5 years, we'll see everything moving. And the dominant movement that we see Actually, the second most important movement that we see, to be technically correct, is this parallax, which is the distance to the star. So the second thing we measure is distance to a star. The first thing we measure, the dominant thing, the most important thing, is actually general relativistic light bending by the sun, which is a really big effect compared to measuring the distance to a star, which is a hell of a long way away.
Hello, it's Kai from Cambridge. How long would it take for it to kind of analyse one star? And like before the Big Bang, what was there and like how did it get there?
Okay, I think there's two questions. The first question is that Gaia will be measuring stars at the rate of about 40 million stars per second, and it'll carry on doing that for 5 or 6 years. So Gaia's going to measure about 1 billion stars, and it's going to measure each one of them about 100 times. So it's going to make 100 billion measurements. And that's a big number. It's quite interesting to think about that number, and you think, how long would it take me to get to 100 billion if I clap my hands once a second? You can work that one out. You'd be quite old and your hands would be very tired by the time you're finished.
Jerry, how many hard disks is that?
If the data were compressed into minimal format, it's about 35,000 DVDs.
So how are you going to store it?
Well, we don't put it on DVDs.
It'd be quite interesting to watch, wouldn't it?
It would be, yeah. Yeah, the modern technology is just amazing, actually. I have a supercomputer at home near my office, which is going to process all this stuff, and we have petabyte scale storage already. But the billion pixel camera is actually equivalent to a high definition film. And so what we're doing is just getting a high-definition movie running for 6 years. So when you say it like that, it's not so bad. I mean, you'd have a hell of a 4G phone bill, but...
Do you ever get tempted while you've got the thing on Earth just to take a few snapshots of things?
Oh, we did.
What did you take a picture of? Yourself? Did you do a selfie with it?
Unfortunately, it's kind of hard to get an image when your thing's that big. So they're really dull test images, but we know the camera works. But it is it's also ultra sensitive, so it's a pretty cool piece of goods. But basically, all it is a video, and from that we have to deduce everything. But we can deduce distances, we can deduce speeds, we can deduce from the colours, we can deduce the chemistry, and so we can just set up a clock and say which bit of the universe formed when and how did it get where it is today, with orders of magnitude more accuracy than we can do before, and including things like finding planets. You know, DDA finds planets by measuring how the speed changes or how the brightness changes. Gaia is going to find planets by actually watching how the sun moves.
Well, hopefully, on the 19th of December, everything's going to go well. So we thought we'd reveal to you some of the technology that's going to be involved in getting it up there.
Yeah, so we are going to launch our very own rocket. We're not going to try and send it into space just yet, but it works on the same principles as a real rocket.
So sticking to our high technology theme, the basis of our rocket is a standard lemonade bottle. I've pre-filled this with one of the fuels which you use in the very high spec rockets, which is hydrogen. So the top of this bottle at the moment is filled with hydrogen. Now, we're getting comments from the front which may be working out what's about to happen next. So hydrogen is a very flammable gas, and it will burn, releasing a huge amount of energy. And when you heat up gas, it gets bigger. And so we have a bottle with a load of gas, which has suddenly got maybe 20 times bigger inside it. We're going to have taken the lid off at this point, otherwise it will get very messy. There's only the hole at one end, so all that gas, which is expanding, can only get out in one direction. And if I push you, you actually push me back. If you push anything, it pushes you back, not necessarily the kind of fight way. If you lean against a wall, it pushes you back, otherwise you'd fall through the wall.
Or if you're sitting on a wheelie chair and you push someone, you'll move.
Indeed, it's a very, very fundamental piece of physics which Newton worked out. And so if the bottle is pushing lots of gas out one way, the gas should be pushing the bottle the other way, and we should have an interesting effect.
So there will be a bit of a bang, so we're going to need people to put their fingers in their ears. You don't have to do it just yet. I will tell you when to do it. Dave's going to open up the bottle and let out the water. And what that'll do is it'll let in some air, because hydrogen's quite explosive, but it gets a lot more explosive when you mix it with air. So we're going to let in a nice amount of air, and I'm going to now put my ear defenders on. And then we're going to put it into our rocket launcher. And Dave is going to light the gases. And everyone put their fingers in their ears now. Come on.
And so that's exactly the same principle which a space rocket works on. You burn actually hydrogen and oxygen, the same thing we're burning here. You liquefy it so you get more in the rocket, it expands, pushes downwards, and the rocket goes upwards. And it works even in space with nothing else to push against.
Any more questions from you guys for any of our panelists before we finish?
Hello, it's Paul from Cambridge. In the earlier discussion about planets, it was mentioned that there's some planets we can't see because it's dark and they're not illuminated. Is dark matter as simple as that, or you make it sound very mysterious?
Dark matter is not as simple as that, no. Some of it is certainly made up from things we can't see but are like things we know. And in fact, the original experiments to measure the weight of the galaxy and deduce dark matter took place just over 100 years ago, and they were deliberately designed to count or deduce the number of very faint stars and planets that must be out there that, with the technology of the time, they couldn't find. And Gaia will find lots of these planets that we can't see just by weighing them. But dark matter is different. We know from a variety of evidence, partly from just weighing things like the Milky Way, weighing galaxies, but also from weighing the universe and from detailed studies of the sound waves and how they propagate through the early universe, that dark matter can't be made of the same stuff as ordinary matter is. So ordinary matter, baryonic matter as we call it, the stuff we are made of, makes up at most a few % of the total mass in the universe. We don't know what this other stuff is. The best guess is that it's a variety of families of elementary particles, sort of new Higgs boson-y sort of things. But it might not be. It might be our theory of gravity is wrong. You know, there's lots of possibilities that's going on. We just don't know what it is. And that's one of the key challenges for Gaia, is to do precision weighing.
Hello, I'm Wendy from Perth, Australia. Can you tell me how far away from Earth the Gaia satellite will be positioned? And once it's completed its mission in 5 or 6 years' time, what will happen to it?
The key thing with Gaia is that it has to be maintain ultra precision and stability. To measure these tiny angles we're talking about, everything has to be absolutely no varying. So it's got no moving parts. It's got to be kept sufficiently cold and stable that the temperature across the whole thing, which is about 3 meters across, changes by less than 1/1,000,000 of 1 degree over 5 years. And the way to do that is to keep well away from the Earth and the Moon. Partly to avoid eclipses, partly to avoid gravity as the Earth and Moon change from shaking you around. And so real precision satellites, and Gaia will be the fourth of these that's done this, go out to a point 1.5 million kilometres beyond the Earth, which is where the gravity from the Sun and the Earth and the Moon basically more or less cancel out. And so it's a nice stable place. You're far away from the Earth. You can step off to one side a bit and avoid eclipses, so you get no temperature changes. The sun's always illuminating your solar panels. You can always see the Earth to communicate with the Earth, but it's nice and cold and stable. So there have been 3 previous satellites, 2 cosmology ones and 1 infrared one called Herschel, that have used this L2 point. Gaia will do the same, but this L2 point is not actually stable. It's only semi-stable. So if you leave something there for long enough, it'll come and fall on your head. And these days, space agencies are responsible. So when satellites die, they get thrown into an orbit such that either you know what that orbit is very accurately, or that orbit is so far away that you never have to worry about them coming back to Earth. So just about 3 weeks ago, the previous occupant of the spot, which was the Planck microwave background satellite, got thrown out of this place and is now in its own orbit around the Sun. The same with Herschel, and the same with WMAP, an American one, which was there before that. And Gaia will do the same thing. So in 5 years' time, Gaia will become its own satellite of the solar system. And in fact, will be, with these other things, artifacts that survive longer than the Earth does. So when we come to the end of the solar system, the Earth will be burned up to a cinder. But anyone who came to look would find Gaia out there.
It's a comforting thought, isn't it? One last question.
Hi, it's Mira from Cambridge. What theory do you believe in, like how the Big Bang theory started and how it created everything?
That's a really interesting question, actually, because it underlies the whole way one approaches science. And the key idea is not to believe in anything. My whole approach to doing science, and one that I would recommend to anybody, is never to say, I think this is the answer, I wonder if it's true. The key approach is to look at something and say, why did that happen? And then work it out. And you should do that for everything. An amazing number of people have no clue what happens when they turn on a light switch because they've never stopped to think, why does that happen? It happens because it always happens. Well, that's not the real answer. It doesn't happen because it's always happened. So if you just keep asking yourself, why is it so? Then one day we'll get to answer these questions. Now, none of us knows the answer to your question. It's quite possible that you might answer that question one day. Someone of your generation is more likely to answer that question than any of us today. But you'll only do it by keep asking, why is it so?
Please thank our panels this evening. Didier Hello, Alan Tunnicliffe, Joe Gilmore. Thanks also to Dangerous Dave and Ginny Smith over on the experimental side. So this has been a special episode of The Naked Scientists from the Cambridge Science Centre. We'll be back doing more of this in the new year. I hope you've enjoyed yourself. The Naked Scientists is supported by the EPSRC, by the Wellcome Trust and the STFC. I'm Chris Smith. Thank you very much for listening. Have a wonderful Christmas and goodbye.